Welcome to example number 13. We're looking at the physics of a rolling bowling ball. So we have a bowling ball with a mass m and it has a radius r, and it rolls without slipping down a ramp that is inclined at an angle theta. We're going to treat this ball as a uniform solid sphere. So that means we're going to ignore the little finger holes that you have on a bowling ball, and we're just going to treat it as a uniform solid sphere. First part, we're going to be drawing a free body diagram for the bowling ball. Part B, we're going to determine the acceleration down the ramp. That's the acceleration of the center of mass. Part C, we're asked to find the force of friction that's acting on the bowling ball that makes it slide and roll. Actually, not slide, but roll. And part D, what is the minimum value of the coefficient of static friction? It's static because remember, it's not slipping down the ramp, it's just rolling down without slipping. Okay, since we have a uniform solid sphere, we need to be using the rotational inertia for a solid sphere. And so we need to look that up. And you can see from our table earlier in the notes that a solid sphere is over here in the bottom left. And we're going to be using this rotational inertia for the solid sphere. So I is equal to 2/5 mr squared. So let's go to part A. Let's draw that free body diagram for this rolling sphere. So what forces are acting on this solid sphere, bowling ball? Well, we have the center right here, and hopefully you realize that the force of gravity is acting on this directly down. So I'm going to label that as Fg, force of gravity acting on it. What else do we have? Well, since it's on a surface, there must be a support surface coming from this ground. And so we'll label that force the normal force. And hopefully you can see that the ball would be rotating this way around. In fact, it'll be angularly accelerating in that direction, in this counterclockwise direction. Then there's got to be a frictional force that's causing this to rotate. And that's going to be going parallel to the inclined plane up the inclined plane. And we're going to label that F sub s. That's the force of friction. And this is actually a static frictional force. Okay, so now we're ready to apply our equations of Newton's second law for this object. Now we can apply Newton's second law as treated as a single object moving with this, or a single particle right here, and we're looking at this accelerating down the ramp. Because as you can imagine, if you were to treat the ball as a single particle, it is really accelerating parallel to the ramp in this direction. So the center of mass right there is moving at this constant acceleration, a center of mass. So we can apply the translational version of sum of F equals ma, and we're going to be using the acceleration of the center of mass. And we can also apply the sum of the forces in the y direction, and hopefully you can visualize that if we look at along our y-axis. There's our y-axis and there's our x-axis. There is not going to be any acceleration because it's not accelerating vertically because we've tilted our axes. Remember, our x-axis is down the ramp and our y-axis is actually perpendicular to the ramp. So, what forces are acting on it along the x-axis? Well, you can see that there's a force of friction that is going in the opposite direction of the acceleration down the ramp. And there's a component of this force of gravity. Let's make the force of gravity a little bit bigger so that it should be, at least realistically, the x component of this gravity should be bigger than the force of friction here. So we're going to need to break up this force of gravity into two components. We have a component that is going right along the y-axis. We can call that F sub g y. And then we have the x component, we'll just draw up here, going parallel to the inclined plane. And we're going to label that as F sub gx. And this should be actually larger than this. So along our x-axis here, we'll have fgx, right, moving down the ramp. And then we have the force of friction going parallel up the inclined plane, and then we have equals MAC. That's the acceleration of the center of mass. So we should obviously write this in terms of m and g, because Fg equals mg. And then we have an angle theta in here. And if you look, this is 90 degrees, and then this is 90 minus theta. And that will, if you look at over in here, that angle over here is going to be theta, which will make the same angle over here to be theta as well. So therefore, what is Fgx and Fgy? Well, Fgx would be the opposite side of this, and so we'll be using the trig ratio sine theta. Sine theta is equal to opposite over hypotenuse. So Fgx we can rewrite as mg times sine theta. So we'll replace that over here with mg times sine theta minus the force of static friction is equal to m times a of the center of mass. If you look along the y-axis, the y component of gravity, Fgy, will be balancing out the normal force, and that's not drawn properly there either. And we should see that the normal force will be equivalent to the y component of the force of gravity. So Fn minus Fgy is equal to 0, and so the normal force is equal to Fgy. Which trig ratio would you use here? Hopefully you're seeing that this is the adjacent side of this right triangle. Remember, this down here is the right angle. So that's going to be mg times cosine theta. Okay, so we've got a couple equations to develop here. Now we need to use the rotational inertia. And we're going to use the sum of the torques is equal to I times alpha. So it is accelerating angularly. Okay, so we need to pick a pivot point, a point of rotation, and a suitable one would be right around the center of mass. So we're going to use this point P as our point of rotation, and we're going to do the torques about point P. Now, if you look at it, you have several forces: the normal force, the force of gravity, and the force of friction, right? But some of the forces won't produce any torques. You see, the normal force is acting right along this line of action, right along this dashed line right here. So really, if you look at the torque produced by the normal force, that's going to be, let's say, Fn times r, but the angle is going to be sine of either 0 or 180 degrees, and that's going to be essentially 0. So there's no torque produced by the normal force because it's acting right along the radius of the sphere. The force of gravity, if you look at the torque from, let's say, g for force of gravity, that would be the force of gravity multiplied by the distance from the point of rotation. But the point of rotation is right at the center of gravity, so that's 0. So that whole torque is going to be, I guess I could put theta in there, but don't worry about that. There's not going to be any torque produced by that because this distance is 0. So there's no torque produced by the normal force, there's no torque produced by the gravity, but there is a torque produced by the force of friction. So the force of friction, static, does produce a torque. It's going to be multiplied by this distance, which is r, the radius. And the angle that it's acting at is 90. So you can put it in sine 90, but sine 90 is, guess what? 1. And that's equal to I of a solid sphere, which is 2/5 mr squared multiplied by the angular acceleration. Now we want to relate the angular quantities to the linear quantities. And if you recall, the acceleration of the center of mass is really equal to the radius multiplied by the angular acceleration. So let's replace this angular acceleration with the acceleration of the center of mass divided by the radius. So we're going to have the force of static friction multiplied by r equals 2/5 mr squared multiplied by a of the acceleration of the center of mass divided by the radius. And you can see some cancellations that occur. You should see that this r will cancel with one of those r's up there, but then there's an r on both sides here, so that r will cancel out completely. So the force of static friction is really equal to 2/5 m times A of the center of mass. And hopefully you can see we've got three equations, one here, and then one here. I'd like to get an expression for the acceleration in terms of theta and g. How are we going to do that? If we look over here, we got an mg sine theta. We have a force of friction and then ma. And then I have a force of friction over here. So I'm thinking I'm going to, let's call that equation 1. This is 2, and this is 3. I'm going to sub equation 3 into equation 1. Okay, let's replace that into here. And then you'll see I can collect like terms of this acceleration here and here. So bringing that term over here to the right side, and then I'm going to add 2/5 plus 1, which is like 5/5. And then I'll get 7/5 ma, and you can see that there's an m on both sides, so the mass cancels out, making the mass independent in our answer. And so then solving for the acceleration of the center of mass, and we get this nice expression for the acceleration of the center of mass of the ball. So that's exactly how much this ball is going to be accelerated at 5/7 g sine theta. If this was just an object with mass m and that didn't rotate at all, the answer would turn out to be just g sine theta. So you'll notice it's 5/7 g sine theta, which means that it's accelerating at a smaller rate than a point mass, or like a box that would be sliding down a frictionless plane. Okay, so we've answered part A. There's the free body diagram over here. And now the answer for part B has been completed. It's right over here. So let's move on to part C. What would be the force of friction acting on the ball? Now we have it over here. My imagination thinks I'm going to actually take this and replace that into there so that I get actually an answer that is not in terms of the acceleration, but in terms of g and sine theta. So let's replace this equation into here. And then we can cancel out the 5's. And there we go. We have the answer for the force of static friction acting on the ball. So we've answered part C. And then part D is determining what the minimum value of the coefficient of static friction, so that when the ball is going down here, it's rolling and it's not slipping. So you have the frictional formula here, and you have the normal force. What's the relationship between the friction and the normal force? And hopefully you're thinking the force of friction is equal to, it's actually less than or equal to, mu sub s times the normal force. So we're going to place this expression over here on the left side and this expression over here on the right side. And then we can cancel out the mg's, making it independent of the mass. And let's divide both sides by cosine theta, and we'll get 2/7 sine theta over cosine theta, which is really tangent theta. And so we'll put a box around that answer, and that's the answer for part D. So to prevent slipping, the coefficient of friction must be at least, so really there is a greater than or equal sign here, at least equal to 2/7 times tan theta. So if the plane is very tilted at a very small angle theta, then you don't really need a lot of friction. But as the angle gets larger, as theta gets larger here, then you're going to need more and more static friction for it to not slip. However, suppose that, the angle was so big and mu wasn't large enough, then what would happen? Well, then you would get slipping. And that's really a whole new different type of problem. And we're not going to treat that in this course, but if you're interested, you can take Physics C. And that's it for example number 13.